Okay, so thank you for the opportunity to give this talk. So the talk will be about operator methods for modeling of waves and plasmas. And this is, I have to tell you, this is actually an applied problem. And to explain this problem, I will have to give an extended introduction into what plasma physics is really, what this application is really about. So I will start with an introduction into the theory of plasma waves. And usually it takes me, half a year. I teach a course on plasma waves. It takes me half a year to explain this, but I will explain it in 5 minutes to you. Then I will move to the actual Koopman methods, okay? And the point that I will try to sell in this talk is that, in this applied problem of modeling waves in plasmas for actually practical applications, Koopman methods are not just convenient, they are probably the methods to use. And I will try to convince you in this. So I will mostly talk about linear waves. And about calculating the linear conductivity of inhomogeneous plasma. I was also going to talk about the quasi-linear theory, including small nonlinearities in this problem. And I have these slides, but I don't think I will have time. So I guess I will just skip this part. And one comment I want to make is that this is really a work in progress. Okay, this has never been published yet. I'm actually very excited about this conference because I started to work on this like a year ago. And then I realized that what I'm doing is actually application of Koopman methods. And then this conference came up and I'm actually really excited about this and the timing is perfect. So don't laugh. I will start with a kindergarten slide, which, I have to say what this is all about really. So as you probably know, one of the ultimate applications of plasma physics is about fusion power, right? So the idea is that you take hot, dense plasma, stick it into a confining device, and keep it there for a sufficiently long time. And then, if you have hydrogen plasma, then you will have fusion reactions, they will release energy, and then you get yourself electricity out of that. So the trick here is to create a plasma for long enough pressure and for a long enough time. And there are different ways to do that. So one of the ways to do it is to use magnetic confinement, and particularly tokamaks. So this is an example of a tokamak. A tokamak is basically a donut-shaped plasma confined with external magnetic fields and also magnetic fields created by internal current in this plasma. And the trick is how to keep this plasma hot and how to control its dynamics. Okay, and waves are actually essential for this. So every tokamak comes with its RF radio frequency system, typically more than one. And these systems work in 3 different frequency ranges. Ion cyclotron frequency range, which is tens of megahertz. Then there are electron cyclotron frequencies, which is around 100 megahertz. And there is so-called lower hybrid regime, which is geometric mean of the two, essentially. And just for fun, so this is a picture of a panoramic view of interior of a tokamak showing two wave systems. So this is a system, this is ICRF antenna, which is supposed to work in this frequency range. So you basically drive currents along these copper wires, and then AC currents create waves, and the waves propagate into plasma, and the plasma is in front of the picture. And so this is another system that is called LH grill, okay, lower hybrid grill. And basically you have a klystron in the back of the plasma, which creates radiation, and radiation gets channeled into the plasma through waveguides. And what you see here is a mouth of the waveguide system. And then electron cyclotron waves are produced by, typically by gyrotrons, which use relativistic electron beams. So there are 3 different technologies which use different frequency ranges, but really, it's all about solving Maxwell's equations. And The Maxwell's equations are usually written as equations for the electric field, and the electric field is typically considered monochromatic in time. Okay, so because plasma evolves, but plasma evolves on time scales that are irrelevant for these RF problems. And so the problem is to solve this equation. So this equation involves the dielectric operator, which is related to the plasma conductivity. And so this equation describes all three types of waves, but depending on what kind of waves we're using and depending on the frequency range, the approaches to solving these equations are actually very different. So in one case, for example, electrocyclotron waves and lower hybrid waves, they usually come in the form of beams. Then it's convenient to use the geometrical optics approximation. So basically you calculate rays, geometrical optics rays using ray equations, and then you calculate the intensity along these rays using simple formulas that I don't need to explain. And then what you really need in the end is to calculate the absorption power. So the absorption power is essentially determined by the anti-Hermitian part of the dielectric tensor. This, however, is often oversimplified. So there are other ways to do things. So quasi-optical codes include diffraction and also are applied to these waves. But most challenging are waves in the ion cyclotron range because you cannot do any asymptotic analysis for them. You actually have to solve the complete Maxwell's equation. And this is what is called full wave approach. So you can see these are typical examples of simulations of waves in this regime. So you can see a wave pattern. So you can see the wavelength. This is a cross section of a tokamak. Simulations are typically two-dimensional. And you can see that there is one wavelength, there is another wavelength if you look closely. And so the waves are very much non-iconal. So that's why the whole PDE is supposed to be, solved as a PDE. And then you calculate the power deposition. The power deposition looks typically like this. So often people say that, Maxwell's equations, right? You solve Maxwell's equations without geometrical optics approximation. This must be an exact solution. It's not an exact solution by any means, because this equation involves a model of, involves epsilon, right? And so you have to, these equations have to come together with a model for the plasma conductivity. And the big question is, so basically there are two questions in the modeling. How do you solve this equation given the conductivity, and how do you calculate the conductivity? So I'm going to talk about the second problem, which is more mathematical. How do you find the conductivity? This is actually trickier than people usually think. Well, in the general case, what you need to solve is you need to solve the Vlasov equation, which is basically the Liouville equation in the mean field approximation. It's an equation that describes the distribution function of each species. So you have this equation for electrons, all types of ions separately. And then waves are typically weak. So how you solve it, you basically say, well, my distribution function for each species will be an average distribution function plus small fluctuations. And these small fluctuations will be of the order of the electric field. And I will linearize this equation, and I will get an equation for F tilde. And I will take the wave-driven Lorentz force and put it on the right-hand side. And I will express the magnetic field using Faraday's law through the electric field. So the right-hand side is basically something times the electric field. And then once I solve this equation, I calculate the current density by integrating over the momentum. And because the right-hand side turns out to be proportional to the electric field, I can infer the conductivity from here. And when there are no external fields, this is easy to do. When there are no external fields and the plasma is uniform, then you basically take the Fourier transform of this equation. You don't worry about this term, and this is trivial. You get you get the result right away. However, the magnetic field is essential, first of all, and then there is non-uniformity. So when the magnetic field is there, this term cannot be neglected. And then what people do usually, they say, well, it's, what is this? This is hyperbolic equation with the right-hand side. So what we're going to do is we will find characteristics of this equation, which are determined by the left side of this equation. And then we will integrate the right-hand side of this equation over these characteristics. And the answer is ugly, but in some cases it is manageable, right? If you have a uniform magnetic field, to calculate this integral is not a big deal. It's really in every textbook. And but then the unfortunate thing is that if you deal with collisionless plasma, and the response of collisionless plasma is very much peaked near cyclotron resonances. Plasma responds resonantly. For example, the interesting thing to calculate is the absorption power, right? And the absorption power actually depends exponentially on the distance, spectral distance to a cyclotron resonance. And if for some reason, well, if the magnetic field is non-uniform, and it is usually non-uniform, if the temperature is non-uniform, if K parallel is non-uniform, then you can easily miss by, a lot, and 100% easily. And then this has to be, so the inhomogeneity has to be taken into account. This was understood in the past. And people, since the 80s, there were papers which addressed the inhomogeneity of the magnetic field. Recently, there was a paper in 2016 which addressed the inhomogeneity of the parallel wave number for these waves. What do I mean by inhomogeneity of the parallel wave number? Well, usually, often, these codes use spectral decomposition of the field. So really, what you're interested in is to calculate a response of a plasma to a basis function, and the basis function is a Fourier mode. These are just cylindrical coordinates that are convenient to use, and they depend on the coordinate L along the magnetic field. So the parallel wave number that you infer from here is simply the gradient of the phase, and so it is by no means a constant. So if you neglect this fact, so if you take that into account, this is the picture that you get. This is, again, a typical simulation of IC ion cyclotron heating. You have a wave propagating from an antenna, and it basically comes and dissipates somewhere here. If you neglect this, then this is the stuff that you get. You get numerical pollution, and it's a big deal. How people got this picture instead of this picture? Well, there have been ways, there are ideas of how to fix these things ad hoc, right? And it's not, but surprisingly enough, waves have been studied in plasmas for many, many decades. But if you look up a textbook, you will never find, not in a single textbook, a systematic theory of waves in non-uniform plasma, because once you include kinetic effects, it just becomes super ugly. And people just don't do it. So you can see that people address certain special cases, but when you want to include them all, the gradient of K, the gradient of the magnetic field, the gradient of the background distribution, the density, the pressure, the electric field, it's just too complicated using these characteristics. And that's where operator methods and Koopman methods become convenient. Let me explain you how. So again, the whole thing is about solving this linearized Lassov equation. So if we multiply this Lassov equation by I, it's a first order partial differential equation. As you know, we can put it in the form that looks a lot like a Schrodinger equation. And that's Koopman's formulation. In a way, this is a driven Schrodinger equation because this is a linearized theory. So it has a right-hand side. And the Hamiltonian that enters here is the Liouvillean. It is given by this formula, and lambda looks cumbersome, but it's really not a big deal. It's just a bunch of derivatives. So I'm not worried about this. I'm worried about this. And really, what we need to do is we need to invert this operator. Okay. Now, for monochromatic waves, in plasma, the nice thing is that you can actually do it. The Green's operator, which is essentially the inverse of this, can be expressed in the formal integral form as exponentiated Liouvillean. Okay, and the integral is from 0 to infinity. And this operator is actually parent Frobenius operator. And again, the conductivity operator will be expressed through the Green's operator and this lambda, which is not really interesting. So it all comes down to calculating this exponent. And there are two approaches of how to do this operator-based method. So wave physics, the plasma wave physics is a lot like quantum mechanics. You basically manipulate operators. Linear operators, and one of them is the to use Weyl calculus. I assume that everyone knows this, but let me just in case remind you or maybe introduce the notation that I'm using. So we're talking about integral operators. Now, integral operators, conductivity is an integral operator. Okay, the integral operators are typically expressed in this form through coordinate matrix elements. You can also introduce a Weyl symbol, phase space representation of this symbol. So the Weyl symbol is basically, which is this, it's basically the Fourier transform of this matrix element after proper symmetrization. Okay, and so the mapping of this operator to the symbol, which is called the Wigner transform, is natural in the sense that it is intuitive. So it maps a unit operator into one, a coordinate operator into a coordinate, the wave operator, the wave number operator, which is the derivative for the momentum, gets mapped to a wave number, and then there is this nice property that this transform commutes with taking Hermitian adjoint. And then, and then there is this nice property that if you want to calculate the symbol of a product, of the product of two operators, you can do the symbol of the product of two operators is simply the so-called Weyl product of their symbols, right? So the star product in the it's expressed as the exponent raised to this funny operator called the Janus operator, or basically it's the Poisson bracket. So it's an exponent raised to the Poisson bracket. And why is this convenient? Well, it is convenient because if the plasma response is non-resonant, which is not the most interesting case, but it is the case sometimes, then it gives you an opportunity to perform asymptotic expansions really easily, because this Janus operator is basically when you have wavelength much smaller than the typical scale of the system, this operator scales as the geometrical optics parameter, so it is small effectively. So you can expand the Weyl star to the first order. Once you have done that, you can express the conductivity symbol through the symbol of the Green's operator and the symbol of that other operator that is not interesting. And then if you use this and substitute it here and recall that this is really just a Poisson bracket, then you get yourself a symbol of the conductivity for free. You don't, there are no calculations. It's all just application of existing theorems. And then calculating an operator from a symbol can be complicated, but you don't really need it in the general case. What you need is to calculate application of the result of an application of an operator to a quasi-monochromatic field. And again, there is a theorem that tells you that if you want to calculate an effect of an operator to a quasi-monochromatic field, it can be expressed in terms of an operator, effective envelope operator acting on the smooth envelope. And this envelope operator can be expressed through the symbol of sigma right away. Basically, it's sigma and it is derivative of the sigma with respect to k. So you calculate the symbol, you substitute it here, that's it. For example, for non-magnetized isotropic plasma, the Green's operator has a symbol which is particularly simple. And then even without any of this, you can actually express this symbol exactly in this form. So it's an operator raised to an exponent. And then if you want to use this approximation, well, you get these additional terms in addition to the textbook formula that only applies in homogeneous plasma. So this is important to keep because these terms are important to keep because this is what keeps the energy conservation. If you neglect this, you will completely mess up the calculation of the power absorption because power absorption is weak. And once you have mixed a strong dispersive effect with weak dissipation, you completely messed up the dissipation. You have to be very careful about keeping dissipation and dispersion separate.
10 minutes left, Ilya.
Okay, this doesn't work for resonant absorption, but for resonant absorption, you can actually do an interesting thing. You can calculate this Green's operator basically using the fact that that the Hamiltonian is just the Liouvillean is just this, right? So you substitute it here, then your Perrin-Frobenius operator becomes just a shift. If you apply it to a quasi-monochromatic field, it shifts both the phase and it shifts the envelope. The envelope is weak, is smooth, so the envelope can be Taylor expanded, and then you can express the final result in terms of this integral, which is not an operator, just a function. And then you can calculate this function to any order you want. And actually, if you neglect, it's very easy to see that if you neglect gradients of the wave number, you completely miss the the absorption. So these effects are important. And now this is like the crown jewel of this whole theory, which is not finished, but we really need to apply these to the to magnetized plasma. Now, for magnetized plasma, this is all messed up because the Liouvillean contains two terms now, and they don't commute. So this contains d by dp, and this contains p. And if you want to raise to exponentiate this operator, then it's really hard. However, what particles do in a tokamak, they travel along these trajectories, which are basically spirals around smooth trajectories called guiding center trajectories. So what you can do is you can transform to the guiding center coordinates using a unitary transformation. And then your guiding center Hamiltonian is very simple. And then you substitute this into the Green's operator, and you express your Green's operator in terms of guiding center Green's operator. Guiding center Green's operator depends on the guiding center Hamiltonian. And the guiding center Hamiltonian contains terms that commute only weakly, do not commute, whose commutator is small. Okay, and really we are only interested in application of these operators on Fourier harmonics. And so in the end of the day, we need to calculate operators like this. And because operators in the exponent do not commute only weakly, you can use an asymptotic expansion. You can neglect higher order commutators, and you can express this operator in a tractable analytic form in the very general case. Don't need to assume anything. It's just a matter of doing this algebra. It's a lot of algebra. I haven't done the whole algebra, but it's very easy to. But it's easy to see that it's doable because and here you have the same operator which we had for non-magnetized plasma. Here you have magnetic drifts. Here you have diamagnetic forces. And the thing is, it's doable. So it's an asymptotic theory that works in the general case. Like I said, I don't have time to talk about quasi-linear theory, which is actually even fancier, to be honest. But I'll just jump to conclusions. So the point is, plasma wave simulations typically rely on analytic models of the conductivity. Even when people say that they are solving exact Maxwell's equations, they really don't. They need models for sigma. And calculating sigma using a traditional machinery of plasma physics is difficult, just technically difficult. But if you put this in terms of this Liouvillean, form, use Perrin-Frobenius operator, it all becomes a matter of manipulating linear operators. And then the whole bunch of formulas that you can just take from a textbook and apply. This looks even nicer for nonlinear waves, but I didn't really have time to do this. A lot of work remains to be done, but the message is that I think this is maybe the way to do the wave theory for inhomogeneous plasmas, and which doesn't exist, but asymptotically, it's just a matter of algebra, and the algebra seems doable. So I will stop here and thank you for your attention.
Let's thank the speaker. Very nice talk, and we have 5 minutes for discussions. So, yes. So Marek, please go ahead.
Hi. Could you repeat why those operators after the guide center transformation commute suddenly?
They do not commute, but the commutators are small.
But are they small as applied to the typical test functions where you will be considering the propagation, or?
Well, they are. Of course, this does not work in arbitrary fields, but it works in machines where the guiding center of these orbits is small, and the variation. So the typical scale of the magnetic field is, I don't know, a meter, let's say. This size of these orbits is, well, millimeters. Depends on which species you apply this to. For alpha particles, it can be a few centimeters, but you have a small parameter in the system, which is, in this case, it's a gyro radius to the size of the machine, and that's why it's nice. There is a trick here that, when you calculate the guiding center transformation, there is a gradient that enters this thing, and this gradient actually it comes well, because you apply this whole thing to a field, to a wave field. This is determined by the wavelength, and the wavelength can be really small. So I'm not saying that the gyro radius is much smaller than the wavelength. No, I'm saying that you separate. So you separate the guiding center motion and this u. So then you calculate the guiding center motion separately. It doesn't involve any rapid oscillations. It doesn't know anything about the wave. This operator can't care less about the oscillating field. And all the large gradients are now absorbed in this operator u. And for this operator u, you can be in two different regimes. Either this thing is small, which is often the case, and then you really expand this, simply do Taylor expansion. Or if this thing is large, which also happens, then you can do the Taylor expansion. Then you can do the Weyl expansion as I did here. So you calculate the symbol, you calculate an expansion of the symbol. So there are limits. By doing guiding center theory, you introduce a small parameter. That's the message.
Thank you.